1800 UT. So I will kick it off. Hi, everybody. This is Bob Buckheim, president of SAS, welcoming you to episode 4 of the SAS-AAVSO Joint Symposium online this year. I am delighted that you're all with us and have been thrilled at the response so far on the symposium. We've got people literally from all over the world, from Australia and New Zealand to Hawaii, North and South America, UK, Europe, and India. So all different time zones are accounted for. And I thank those of you who have sent emails with compliments for the production team and your pleasure in participating in this symposium. You know what, Bob? Gil?
Yes.
We've got the wrong slide set up here.
I know. It's just go to the next one.
Okay. Oops.
There you go.
Okay. Those of you who...
Welcome to day 3.
Yeah, day 3, episode 3. For those of you, there may be a few out who are not familiar with the American Association of Variable Star Observers. Stella Kafka's webcam is on. Stella is the executive director of AAVSO. And as I mentioned, I'm the president of the Society for Astronomical Sciences. I encourage you to check out the websites of both organizations to see the assets and features that both organizations will offer you. As Arnie Hendon once said, our partnership is sort of a marriage made in the stars. Also, I thank those of you who have sent me emails with some criticism and suggestions so that we can try to improve things day by day as we go through this 5 sessions of the online webinar. I'm going to touch on a couple of those in a moment. By now, most of you are fully trained professionals in the use of GoToWebinar, so I won't belabor this. During the session, the system has muted your microphones and turned your webcams off. But if you would like to get a message to one of the presenters, you have 2 options. One is the raised hand icon. The other is to type a question into the questions box. After each presentation, Wayne Green will be watching for both raised hands and questions, and will recognize you and unmute your mic so that you can give your question or comment to the presenter. That little GoToWebinar control panel will automatically minimize itself within a few minutes. If it does and you want it back, you click that red arrow and it will come back to life for you. Yes, the session is being recorded. The recording will probably be available late, I was going to say this evening, but it depends on your time zone. 4 or 5 hours after the session ends, the recording should be available. You just, I think you just hit the same link that you used to join the webinar today, and it'll take you to the recording. I have been asked about the printed proceedings. Yes, there will be some. The printed proceedings book is a membership benefit in SAS. On request, you will get one. I haven't figured out yet how to receive and keep track of those requests, so stay tuned. By next weekend's session, I'll have an answer to how you order one. The production team has been mentioned. Bob Gill is handling all the presenter slides, so he's our AV guy, as he usually is during the live symposium. Jerry Foote is the master of ceremonies. He'll be introducing all the speakers, and he is still the man with the hook who will pull them off when their time is done. Wayne Green We'll be working mostly behind the scenes, watching for questions and comments and any technical issues that people are having. He will try at least to help resolve them. As always, I want to recognize and thank our sponsors and vendors. DC3 Dreams, you heard from yesterday. Software BISC will be giving an infomercial next weekend. Sky and Tel, Woodland Hills Camera and Telescopes have been longtime loyal supporters of SAS field tested systems. Tom Field will also be giving an infomercial next week, so you'll hear from him about the RSpec software. And our vendors, Optech, Observatory Operators, Hyperion Astronomy, Planewave Instruments, and Starlight Express. When it's time to buy some new gear for your observatory, we encourage you to take a good look at the fine products from these loyal supporters of SAS. Stella, would you like to welcome on behalf of AAVSO?
Absolutely. So hello, everyone, and welcome on episode 3 of this Marathon of Science. We have an absolutely amazing schedule for you today, and I would like to add my thanks to the power team that is organizing this, Bob, Gwen, and Jane, and Jerry. So with that, just looking at the schedule, today we're going to be moving from smart techniques for data processing to rocks in our solar system, to rocks around stars outside our solar system, to hot A and B stars from Tess and Bright, to star clusters, you name it. So we have a very interesting buffet from which to eat. And I would like with that for you to sit back, relax, and enjoy the ride. So have a really good meeting, everyone, and be safe.
Hey, Jerry, it's all yours.
Okay, thank you very much. I'd like to first introduce Daniel Parrott, Tycho Tracker, software for minor planets.
Thank you, Jerry. Okay, so hello, my name is Daniel Parrott, and today I'm going to be presenting the Tycho Tracker software. This is software that's been developed for the detection and measurement of minor planets. And so one of the main features of Tycho is that it facilitates the discovery of asteroids. And so to that end, I would like to just provide a brief overview of the history of different detection techniques for asteroids, and then follow that up with a discussion on synthetic tracking. What is synthetic tracking? Why might you use it? And then also a discussion on advancements that have recently taken place to make synthetic tracking a viable technique. And then if you are interested in discovering asteroids, you might want to know what kind of criteria, what kind of factors to pay attention to. And so again, just a brief history here on these detection techniques. So the blink comparator was first invented in 1904, and the most notable discovery was that of Pluto in 1930. And this technique works by taking 2 images, 2 photographs of the same area of sky, taken at different times of the night. And by rapidly switching back and forth between these 2 images, it helps to make moving objects observed. Now, it's not a commonly used technique today, simply because computer algorithms are more efficient at detecting these moving objects. And so in 1983, Tom Grills and Bob McMillan founded Spacewatch, and they were the first to make use of charge-coupled device technology, CCD camera technology, in discovering asteroids. And the way this worked was they would take 4 exposures, again, of the same field of view, typically 15 to 20 minutes apart, and then software would then automatically extract and remove stationary objects, such as stars, and then the remaining objects would be those of interest, the moving objects. And by and large, this is the technique still widely used today, even with the professional surveys. Now, another technique, and I added just this one here just because it's somewhat interesting, the Sloan Digital Sky Survey spends most of its time surveying galaxies and quasars, but it also captures sources in our own cosmic backyard. And so the way this works, it's fitted out with color filters. And so moving objects would be presented differently than stationary objects. So in the picture below, you can see in the left edge, there's a stationary object, a star, and in the center of that picture, you can see a moving object as it has exited from one filter to the next. Now, all detections require a minimum signal to noise ratio. And when that ratio is too low, the object appears indistinguishable from that of noise. And so all of the techniques that I've talked about up to this point are limited to the signal to noise ratio of a single exposure. In other words, they do not stack the exposures. So if you have a telescope or an instrument with modest sized aperture, and you would still like to be able to detect those faint objects, then stacking becomes necessary. And so here you would then stack images with a motion offset. And this also helps to eliminate what's called trailing loss. So trailing loss is what happens when you have a longer exposure and the object becomes streaked. And so with the longer exposure, noise continues to build up, noise continues to accumulate, but the signal of the object is spread out across multiple pixels. And so the resulting signal to noise ratio is actually decreased with the longer exposure. So the way to mitigate that is to take several shorter exposures and stack them. Now, I'm sure most of us, or at least some of us here, are already familiar with this concept. There are different terms for it, but track and stack, shift and add. This is a concept whereby it's mostly used for follow-up, and that's because it requires knowledge of the motion of the asteroid in advance. So you have to know the motion of the object. Now, it does improve the signal to noise ratio, and the result is that the stars become streaked and the tracked object then appears to be stationary. Now, again, this is not the same as using the mount to track the object, and instead you're still using sidereal tracking. You're still going to have the mount track the stars, but in software, in post-processing, the images will be, again, stacked according to the motion of the object. So here is an example of shift and add. And again, it's just one motion vector. But as you can see in the picture, the stars have become streaked and the object itself appears to have been tracked. And so this is a great way to detect objects that would otherwise be undetectable because here you're able to improve the signal to noise ratio. Now, the question is, let's suppose we still want to improve signal to noise ratio. Let's suppose we still want to detect these fainter objects, but we might not know their motion in advance. And so that's the idea behind synthetic tracking. And so that's the term used here. That's also called digital tracking. So it's useful, again, not just for follow-up, but also discovery, because it can detect objects having a wide range of motion. In other words, it's not limited to just one motion vector. It can explore thousands of motion vectors. And so the way this works is you start off with generating a trial stack for a particular motion vector. And it's called a trial stack because it is one of many stacks. And for each trial stack, you're then going to extract candidate detections. In other words, you're going to run an algorithm to identify objects of interest in that trial stack. And then for each candidate detection, you're then going to assign a quality metric to evaluate how good that detection is. And then you're going to do the above for, again, the thousands of motion vectors, however many you wish to explore, and then sort the resulting detections by quality, and then finally submit the resulting list for evaluation. So as an example, here you can see these are trial stacks of the same object. And so in the center here, this is what you would consider to be the correct motion vector. And then as you get to the edges, you can see that the motion is less and less correct. But these are all trial stacks that would be explored with synthetic tracking. And so it's a very, in fact, it automatically identifies the correct motion vector. So it's a very useful technique. Now, as you might imagine, synthetic tracking is more computationally intensive. However, in just recent years, it has in fact become a viable technique, even for amateur astronomers. And so here I'm going to go over the advancements that have made it viable, starting with the advancements in graphic processing hardware, and then the advent of full-frame CMOS cameras, and then finally the advent of large aperture fast focal ratio telescopes with Hyperstar and Rodda. So in 2013, Dr. Shao of the Jet Propulsion Laboratory was the first to emphasize the use of synthetic tracking for asteroid discovery. Now, unfortunately, at the time, this was largely seen by others as impractical. They ran the numbers and said, well, it's too computationally intensive to be a practical strategy. But in 2013, the reference GPU, graphics processing unit, was a Tesla K20C. Now, that's not to be confused with the automotive company. This is a product of NVIDIA Corporation. So this costs $3,200, and it scores 12,000 on the CUDA benchmark. This is a benchmark that evaluates and ranks different graphics cards. Now, fast forward 7 years later, and now for $1,200, you can get a card that scores 162K on that same benchmark. So what I'm getting at here is that for almost a third the price, you can get computational processing power that's 13.5 times faster. It's an order of magnitude faster. I mean, this is enormous. I wish telescope optics could have the same kind of improvement and capability. So another advancement is that with the full-frame CMOS cameras, so synthetic tracking works really well with short exposures, and I define short as being 30 seconds or less. However, short exposures tend to require low readout noise, and CMOS cameras happen to have that, but traditionally they've been available with just a very small sensor area. But just in the last year, Sony released the IMX455 sensor, which is 60 megapixels, true 16-bit, and it's available in 2 different cameras for the amateur astronomer. Now, another advancement here then, of course, is availability of large aperture telescopes, fast focal ratio. So Hyperstar has been around for a while, but Rowe Ackerman Schmidt Astrograph, that's relatively new. So Hyperstar is sort of a modification to an existing telescope. It works with a normal Schmidt-Cassegrain telescope, and it achieves f1.9 focal ratio. Rodda is optimized for imaging. In fact, you cannot use it for visual purposes. It has f2.2, and on paper, the advantage it has over Hyperstar is it offers a larger imaging circle. So, okay, let's suppose you are interested in discovering asteroids. So what kind of criteria, what kind of factors should you pay attention to? So first, you have limiting magnitude. You really do need to detect those fainter objects. And of course, you have to have good sky coverage. And then finally, the cost to achieve the above. So we want this to be a cost-effective survey. So limiting magnitude, synthetic tracking enables a C14, that's a celestron 14-inch telescope, to regularly achieve magnitude 21. And this is shown by astronomer Mark Holbrook, who I've collaborated with. And the question is, how important is limiting magnitude? So as an example, we have 2 survey telescopes, 703 and G96 at Catalina Sky Survey. So 703 has a larger field of view, 20 square degrees versus 5. So on paper, it should capture 4 times as many discoveries, but in fact, it only captures 1/5 as many. So why is that? Well, 703 has a limiting magnitude of 19.5, whereas G96 has limiting magnitude of 21.5. So 2 magnitudes makes quite a difference. And you can see that on the chart here. So this is a chart of number of discoveries per survey in calendar year 2019. So F51 is Pan-STARRS, that's a 1.8 meter telescope. They reach magnitude 22.7. And I just talked about G96. F52 is also Pan-STARRS, but they're a new installation just coming online. 703, I just mentioned them as well. And T08 is Atlas. So Atlas is well known for having a good sky coverage, high cadence, but they only reach magnitude 19. So limiting magnitude is important. Of course, by itself, that is not sufficient. So you must also actively scan huge portions of the sky. Now, nothing is free. So synthetic tracking will give you that limiting magnitude, but to do so, it takes a longer dwell time. Now, the solution is to use an array of telescopes. Now, you might think that's going to blow the cost part of the equation out of the water, but let's take a look at that. So cost of aperture increases exponentially with size of mirror. I would love it if a 1 meter telescope simply cost twice as much as a ½ meter telescope, but that's simply not how it works. So let's take a look at an example here. So G96 versus an array of modest sized aperture telescopes. So G96 takes 120 seconds to capture 4 30-second exposures, and each field is again 5 square degrees. So therefore it has an efficiency of 120 seconds for that 5 square degrees, and that works out to 24 seconds per square degree of sky. Now, if we wanted to have an array of modest-sized aperture telescopes, let's start with just one of those telescopes. So a single RASA 14 paired with an IMX 455 should reach comparable magnitude in 790 seconds. So we said G96 will reach its magnitude in a 30-second exposure, because again, those exposures are not stacked. And here we're going to take 790 seconds to achieve comparable magnitude. So, and with that sensor, it will achieve 4.5 square degrees and have an efficiency of 176 seconds per square degree. So that being said, if you had an array of 8 of these instruments, then that should work out to an efficiency of 22 seconds per square degree. And if you figure out the cost of this, let's suppose some budgeting for mount, camera, and telescope, it's $30K per instrument, and then 8 of those, 240. And then you budget for computing hardware, and then finally say $500,000 for a roll-off building to house them. You're still under $1 million, and that's still an order of magnitude more cost-effective than a custom 1.5 meter instrument with a custom camera. So example here, as you can see in this diagram, we have a roll-off building, again, to house this array. Roll-off building is very efficient for this purpose. And so again, Tycho tracker, this has started development in 2018, and it also supports, in addition to synthetic tracking, you can generate light curves, determine rotation periods, identify orbit linkages, and of course do follow-up observations of asteroids as well. And so just some examples here with photometry, if you're interested in that with this tool. Here's a raw plot of asteroid 18172, and if you wanted to determine its rotation period, it has a period search module, and then it will show the phase plot diagram of that, and then a periodogram, so you can determine period spectrum and so forth. And so this is a tool that's now in use by several observatories, and I list a few of them here, and then a link to it below. And so at this time, if there are any questions, I'll be happy to take them.
Thank you very much, Daniel. Have you seen any questions, Wayne? You're muted, Wayne.
Hi, Greg. I've just unmuted your microphone. Do you have your question?
You have, perhaps. Can you hear me?
Yes.
Oh, cool. Yeah, I would just, we've exchanged some communications in the past, Daniel and I have, over, but it's been quite a while. I have a 1060 GPU instead of a 1080. Will Tycho run on that, or does it require a 1080?
Well, when I first developed Tycho, I actually developed it with a GTX 970 card. That's an older card.
Yeah.
Yeah. And so it should work with that. The main consideration is the size of the data set that you wish to process. So you want to look at the video memory and so forth.
Okay, thank you.
Does anyone else have a question? Here we got a couple, let's see, no more raised hands that I'm seeing.
Yeah.
Any questions,
Yes.
panelists?
I do actually have a question. This is Greg Sivikoff. Can you hear me?
Yes.
Excellent. So as more and more GPU needs get increased, do you see any possibilities of developing a service where people could use cloud GPUs as opposed to their own GPUs to make this more accessible to people?
Sure. Actually, I have experimented with a Google Compute Engine. So you can spill up a virtual machine, and in fact, with that, presently they offer a V100 GPU, and that's a very high performance GPU. So in essence, you can actually do that today. You could load up the Tycho software on Google Compute Engine, and again, you would basically be renting time on Google to run their cloud services. So that's kind of one thing that's already available.
Thank you.
Wayne, I
We
see
have a-
George Lawyer has his hand up.
Yes. Okay, George, I'm going to go ahead and I'm opening your microphone.
Hi, just wanted to ask, I'm looking through the paper and didn't hear anything about how you find the software. Interested in using it and working with some of the folks at my observatory to try this out.
Sorry, what was the question?
How do we find the software? How do we get the software?
Oh, okay. Well, the website is tycho-tracker.com. There should be on the PowerPoint at the very second to last slide, I believe, was a link to it.
Oh, okay, missed that. Okay. All right, thank you.
Thank you.
Any questions from any of the panelists?
Well, Pablo and John Hoot have raised their hands. Let's open the microphone for Pablo. Hello, Pablo, do you have any questions for us?
No, I have a testimonial because I've been using that program for a couple of months now. It's just amazing what you can do with it. I've been discovering in my old data all kinds of NEOs and not new, but I've been able to track already reported NEOs and comets and everything else. And it's extremely easy to use. And as long as you have a GPU, it's quite fast. And I've been going back 4 years of data that I have 4 years. And if you go to his website, he has videos that explains everything on how to do it, how to report to the Minor Planet Center. It's amazing. It's an amazing program, the capability that it has. That's all I have to say. And I'm a low-level astronomer, amateur astronomer, no astronomy background other than what I've been doing as an amateur astronomer. And you can use just about any telescope and any old data, you can discover all kinds of things. It's really an amazing program.
Thank you, Pablo.
Okay, and John Hoot.
I was curious if anybody has run this on AMD iron.
Yes, I have received from some emails. There are some folks who have had success with the AMD, and so in theory, it should work on an AMD platform.
Does that include AMD accelerators or just the cards listed on your webpage?
It would include AMD accelerators, yes, the AMD GPUs.
Excellent.
And it uses the OpenCL API. So CUDA is more NVIDIA proprietary. But OpenCL is supposed to work with both NVIDIA and AMD.
Okay.
Thanks, John. I think we got all the questions answered. Are any questions from the panelists? Next question is. A couple showing up here on the web. What is the minimum session link cadence, say, for an 8-inch telescope to be useful?
Well, again, it all comes down to signal noise ratio, I guess, and it depends also on what kind of object you wish to detect. So if it's a main belt asteroid, that's going to require a longer total elapsed time than that of a near Earth object, as far as it has to move a certain number of pixels to be detected. So if you just take a couple minutes of exposure, all said and done, then that main belt asteroid won't move very much. I guess as far as to be useful, I typically will do, 30 exposures, and they'll typically be 30 seconds each, so maybe 15 minutes total.
Okay, and we have another question from John Murrell. What does the software detect satellites, and what's going to be the impact of Starlink?
Good question. So yes, it can detect satellites. I have an example of actually a near Earth object, but it was moving at 1164 arc seconds per minute. And that's actually faster than a satellite in GEO. So a geosynchronous satellite will move 900 arc seconds per minute. In other words, I believe 15 degrees per hour. So if it can detect the NEO, in that case, it'll certainly detect a satellite. Effective Starlink, that's actually one of the advantages of synthetic tracking, is that because it can, it makes use of many exposures. It doesn't matter if one of the exposures is quote unquote bad. If you have a Starlink footprint or trail, and even a couple of those exposures, it's not an issue, because synthetic tracking, typically you'll take again 30 to 60 exposures per field. So it's kind of like what amateur astronomers do with astrophotography. Again, you'll take numerous exposures, and you can do some filtering. You can exclude just the small handful of exposures that have some artifacts in them.
Okay, Jerry, I think we should probably get back on with the program here.
Daniel, thank you very much. This is very intriguing stuff.
Thank you, Jerry.
Thank you. Next, we're going to hear from Owen Dugan. He's going to talk to us about astronomy will not trail off. Novel methods for removing satellite trails from images. Owen?
All right, hi, can you hear me?
Yes.
Awesome, thanks. So hi, I'm Owen Dugan, and this is my presentation entitled Astronomy Will Not Trail Off, Novel Methods for Removing Satellite Trails from Images. 1 second. Shoot, the button for changing slides is not up here.
Click in the lower, there you go.
Oh, okay, thanks. Okay, so my research attempts to address a serious problem in astronomy right now, which is that light reflected from satellites is interfering with astronomical measurements. And this is becoming an increasingly large problem with the advent of SpaceX's Starlink network. Starlink will launch up to 42,000 satellites into space. And although this will be extremely useful for providing nearly global internet access, it will also make it difficult to capture images without satellite trails in them. So unfortunately, satellites affect the brightness of an entire image. Here on the right, you can see an image that was ruined by Starlink satellites, and astronomers predict that these trails will negatively impact astronomy research, will be very challenging to remove, and could even be the end of astronomy. So to address this issue, I developed and coded novel algorithms that automatically detect and remove a satellite trail from an image using only one image. And to do this, I split the algorithm into four key modules. The first one is to pre-process the image. Next, I locate a satellite trail in the image. Then I fit a brightness profile to the trail, and finally remove the trail. And also I have a fifth module that tests the photometry of the image with the satellite trail removed to ensure that the satellite trail is accurately removed. So importantly, all these algorithms are modular and so can be optimized independently of one another. So the first stage is to pre-process the image. And in pre-processing, essentially what I do is I remove stars and hot pixels from the image. This is really important because the stars and hot pixels can often outshine the satellite trail, and this can lead the satellite trail detection algorithm astray. For example, here you can see this this blue trail up here is the satellite trail detection algorithm's guess at where the satellite trail is if you do not remove the stars and hot pixels, whereas this here is the actual satellite trail. And you can see that the detection algorithm is led astray by this extremely bright star right here. So to fix this, I first plate solve the image by uploading it to the astrometry.net native database, which then returns the image's location and orientation in the sky. I then query the Gaia database using AstroQuery to obtain the location of all stars in the Gaia database in my image. And here you can see all these identified stars. The big red blob in the center is a galaxy, so that's why it's all covered up. So then I remove all the stars in the image by identifying the radius of each star and then replacing all pixels within that radius with the nearby background brightness. And so here you can see the image with all the stars removed. Oh, sorry about that. Okay. So next I remove outliers and the hot pixels from the image. I have two stages for this. I first mark pixels that are 4 sigma brighter than the median image brightness as outlier candidates. And you can see all the outlier candidates here. But unfortunately, this marks most of the satellite trail as an outlier, which is clearly unacceptable. So then I have a second stage, which then fine-tunes this by checking each outlier candidate and only selecting those that are 3 sigma brighter than their neighboring pixels as true outliers. So these are the true outliers discovered. And then I simply replace the true outliers with the mean nearby image brightness. And you can see that this is the image with the stars and outliers removed. And you can see that the dominant feature is the satellite trail, which it's inverted color. So next, after I've pre-processed the image, the code detects the satellite trail in the image. To do this, I use a fundamental module, which is piecewise bivariate cubic interpolation. And essentially, this is important because it's really useful to be able to determine the brightness of an image at a point that isn't at a pixel. And in order to do that, you need interpolation. At first, I used linear interpolation, but this isn't effective at approximating a Gaussian distribution. In particular, a Gaussian distribution might have a peak that's in between pixels, and linear interpolation really can't approximate that. So instead, I use piecewise bivariate cubic interpolation. To do this, I first compute a piecewise bivariate cubic fit for the entire image by dividing it into 4x4 blocks of pixels, and for each block, fitting a bivariate cubic to it, and then storing all of these cubics. Then when given a point, I find the corresponding pixel block and the associated cubic and apply the correct, I apply that cubic to the point, and I find the correct pixel block by the pixel block that is closest, that has a center that is closest to the given point is the one that I use for the interpolation. So with this, I then implement a line evaluation algorithm, which essentially, given a line, computes what I call the satellite probability index, which the higher the satellite probability index, the more likely it is that that line contains a satellite trail. So to do this, I take equally spaced steps along the line, and then for each step, I compute the image brightness at that point using the piecewise bivariate cubic fit. And then I sum the mean and median brightness of all these points along the line to get the satellite probability index. This is useful because the median is in particular important because stars can have a line that passes through several bright stars may have a mean brightness that is higher than that of the satellite trail, but the median brightness will still likely be very low because the majority of the points that the line passes through will be still background. Whereas for a satellite trail, the majority of the points along the trail will have a higher brightness than the background, and so the median will be higher. So with this, I then search through all lines which enter and exit the image through a pixel. And for each line, I compute the satellite probability index and select the line with the highest satellite probability index. Now, I call this the recursive base case because it's extremely effective, but it's also very slow. It is an Owen cubed algorithm, so it scales it gets very slow as it scales, and it can take up to 5 hours to run on a very large image. So I use recursive scaling to drastically increase to drastically reduce the processing speed. So what I do is oh shoot, 1 second. Oh, there we go. Okay, so if the image is more than 9,000 pixels, I scale it down by a factor of 4, and I continue doing that until the image is less than 9,000 pixels. Then I apply the recursive base case and identify the satellite trail in the smaller image, and then I scale back out by a factor of 4. At this point, I can tweak the identified image using the higher resolution, the identified satellite trail using the higher resolution image by examining nearby lines, and I continue doing this until I've identified the satellite trail in the full-size image. This is much faster. It's an Owen squared, and it can be like give a factor of several hundred improvement. So this, once I've identified the satellite trail, I move on to fitting and removing it. So at this point, I return the stars and hot pixels to the image, and then I fit a brightness profile to the trail and remove it. For this, I use 4 key modules, which are first, to determine which points are influenced by stars and hot pixels. For this, I simply mark points that are within 1 pixel of the edge of a star or that are inside a star, and pick points that are within 1 pixel of a hot pixel as influenced by stars and hot pixels. This is, for example, on the left, you can here in this image, you can see data that has all these pixels that are influenced by stars and hot pixels, whereas here, when these are removed, you can see that it's significantly less noisy data. So next, I use curve fitting. Now, for many purposes, I can use a polynomial fit, but it turns out that the trail, the satellite trail actually wobbles along its central line, presumably due to atmospheric effects. And so this wobble is very rapid and oscillates widely. As you can see here, here's an example wobble from a trail. And this isn't well suited for a polynomial fit. So instead, what I do is I use a variation of a fast Fourier transform. So I perform a fast Fourier transform on the data and then synthesize an exact fit by computing the inverse transform. Then I take each sinusoidal term and weigh it according to its amplitude divided by its frequency plus a very small factor. And the small factor is simply to avoid dividing by 0. And then I remove a specified number of terms that have the lowest weight. Then this allows a smoother fit that still accurately models the key features of the data. So third, I have a module which performs curvilinear transformations on the image. This is important because the satellite trail can have an arbitrary orientation in the image, and also it wobbles. And so this can make a Gaussian that describes it extremely complicated. So to simplify this, I first perform a curvilinear transformation on the image, where I convert all points in the image to a coordinate system where the satellite trail is flattened along the x-axis. The 2 coordinates are going to be the d parallel, which is the distance parallel along the line, and d perpendicular, which is the distance perpendicular to the line. And the curvilinear transformation is described here. The f is the wobble function for the trail. So finally, I have another module which computes a 2D Gaussian, and given a brightness and a standard deviation, it computes the Gaussian by evaluating the brightness polynomial, which varies along the satellite trail, and then computing a 1-dimensional Gaussian, which varies as a function of the distance perpendicular to the trail and has a constant standard deviation. So with these 4 modules, I first implement wobble fitting. So to do this, I examine equally spaced points along the line, and at each point, I determine the perpendicular distance to the center of the trail. I do this using Gaussian cross correlations. Then I determine which points are influenced by stars and hot pixels and linearly interpolate between these points. And then I fit a function using a fit a function to the trail wobble using the curve fitting, and I feed this into the curvilinear transformation module and transform the image to place the trail along the x-axis. So here it's slightly difficult to see, but if you can see this blue line is this is a satellite trail. The black line is a satellite trail, and the blue line that follows it is the fit of the wobble. And you can see here, for example, the satellite trail wobbles and moves to the right, to the left slightly, and you can see that the blue line accurately follows that. Also, an important thing to note is you can see here a star, but the blue line is not drawn off by that because it is taught to ignore the data points that contain stars. So next, I fit the brightness of the star. Here, I determine the brightness at evenly spaced points along the trail, and then I identify and interpolate between points that are influenced by stars and hot pixels. And then finally, I fit a polynomial to the brightness of the trail. Here you can see an example fit of the data. The data is shown in blue, and the fit is shown in orange. And I feed this into the 2D Gaussian. Finally, I fit the standard deviation of the trail by selecting all pixels that are within 5 pixels of the satellite trail. And then I identify and remove stars influenced by points influenced by stars or hot pixels. Oh, sorry about that. And then fit a 1D Gaussian to these points with respect to the perpendicular distance to the trail. This 1D Gaussian, I then take its standard deviation as the standard deviation of the trail and feed that into the 2D Gaussian module. So once I have all this, I evaluate the 2D Gaussian at each point, at each pixel in the image, and subtract it off to obtain an image with no satellite trail. So for some visual results, on the left you can see an image with a satellite trail, and on the right is the same image with my code run on it to remove the satellite trail. And you can see there is no evidence of this. There's no visual evidence of the satellite trail. This photo is courtesy of Ryan Caputo. Similarly, this photo is also courtesy of Ryan Caputo. And here's another image with a satellite trail. And here is the same image with my code run on it to remove the satellite trail. Now, I also tested the photometry of this algorithm. So to do this, I computed the photometric % error between an image with a satellite trail and an image with a satellite trail removed. And I also computed the photometric % error between an image with a satellite trail. Oh, sorry, I should go back. I messed that up. So I meant to say I compute the photometric % error between an image with a satellite trail and an image with no satellite trail. And then I compute the photometric % error between an image with the satellite trail removed and an image with no satellite trail. So the blue line here shows the photometric % error for an image with the trail compared to the photometry for an image with no trail. And the green one shows the photometric % error for an image with the trail removed. Now this is for 9 stars that lie along a satellite trail. And so the closer to 0 photometric % error, the better. And so the photometric % error, the mean photometric % error for the image with the trail is 0.8, whereas the mean photometric % error for the image with the trail removed is 0.09, which is a factor of 9 improvement. Similarly, the standard deviation of the photometric % error for the image with the trail is 1.1, whereas the standard deviation of the photometric error for the image with the trail removed is only 0.5, which is a factor of 2 improvement. So, oh yeah, okay. So note the 7th star, which is right here. This one has a photometric error that is the same for both the image with the trail and the image with the trail removed. So that means that this star is actually not affected significantly by the brightness of the satellite trail, and that this photometric % error is simply due to intrinsic error in the measurement of the photometry. So that means that this can be an estimate that we can use this photometric % error as an estimate of error that's roughly attributable to intrinsic error. And note that all of the stars that are in the image with the satellite trail removed lie within this intrinsic error estimate. So this I would like to test this on more images, but this is extremely promising. So in conclusion, the novel algorithms allow the satellite trails to be removed with a single image and while preserving photometry. And some key modules I used were removing the star, some key features I used were removing the star fields prior to the satellite trail detection. We're using testing lines using mean and median brightness, recursively scaling images, and fitting the trail wobble. And for future research, I'd like to compare integrated Gaussian fits and standard Gaussian fits. I'd like to compare, I'd like to extend my algorithms to color images and partial satellite trails. And I would like to experiment with techniques for removing larger extended objects in the image, such as nebula and galaxies, and employ deep learning convolutional neural networks to rapidly identify images with satellite trails. And finally, I'd also like to create a satellite removal pipeline so that more people can use this code. Thank you. And if you have images that you with satellite trails, I would greatly appreciate it if you could send them to me, because I need as many images as I can get in order to more generally test my code. You can reach me at owen@duganhome.com. And thank you.
Thank you, Owen. That was a very intriguing presentation and a different approach. Wayne, do we have any questions?
Yes, we do. So I'm going to open John Martin's microphone up. Let's see if I can find him in our list here. Okay, hang on a second. Windows is getting me. Where's John?
I'm now unmuted, Wayne. I think I'm
good. Thank you.
Okay. Thanks for giving the talk, Owen. Now, your demonstration was done with a satellite trail that wasn't very overwhelmingly bright, you know, and particularly with some of these constellations, we're worried about them being really bright. How does your algorithm perform on a much brighter satellite trail? Have you had a chance to try that out?
I haven't tested it on an extremely bright satellite trail, but I believe that it should work similarly. As long as the satellite trail doesn't saturate the camera, I believe that the code should be able to deal with the brighter satellite trails. Although I haven't tested, I don't have an image that has a brighter satellite trail yet to test.
I might have to send you some then. Thank you. And I had one other question actually. How much CPU time does your algorithm take to remove a trail from a single image right now? You're obviously improving it, but I'm wondering what stage you're at right now.
Yeah, so I definitely believe that it can be made more efficient. I haven't really focused on that yet. I've just mostly focused on developing it. But currently it takes, I'd say, about 10 minutes, but I believe it can be significantly improved. It's I haven't been focusing on speed, and except for the fact that the one algorithm was too slow, so I needed to speed it up, the recursive scaling part.
Got it. Thank you.
Yeah, thank you.
Thanks, John. We have a question from Jay Miller. I'm going to open your microphone up, Jay. Okay, Jay, you there?
Okay.
Jay, are you with us? His question is, how long does it take per image, and can it be automated?
Yeah, so for it takes roughly right now about 10 minutes per image, but it should, I believe that can be significantly improved. For example, like right now the slowest factor by a long shot is the bivariate cubic interpolation, which I simply haven't had. I just haven't optimized it yet. I'm sure it can be significantly faster. It just I've been mostly focused on making on experimenting with approaches, and I haven't yet optimized it. And yes, it can be automated. Right now, if you give it an image, it will automatically run on it. And I'm working on making a website that will that you can upload an image and it will, or a set of images, and it will remove the satellite trails for you.
Very good. Very good. Thank you.
Okay. Heinz Eckstein says, shall I open your microphone, Heinz? There. Up. No, it's not letting me open your microphone. Okay, so I'll read the question. Does this work better when the images are oversampled, say with smaller pixels? And have you tried the Huff transform line detection?
Yeah, so for the oversampled and undersampled part, the images I've been using are fairly well sampled. I haven't, I haven't yet. I don't have one of the things I need is more images, so I would like to test it with different amount, like undersampled, oversampled images. But I believe it works. It should work well with undersampled images. I haven't tested it with hugely oversampled images, but I believe it should also work well. And I did try the Hugh transform. It was not actually detecting the line accurately enough. So that's why I switched to this satellite trail detection algorithm.
That's good. Brad has a question for us. Let's see if I open your microphone, Brad. What's your question? Brad, are you with us?
Oh, I am. Hold on. Did you unmute me?
Yes, I did.
Oh, I typed my question in. My question was, I'd love to see, I don't know if you've tried this with artificial satellite trails. My concern is what this is doing to the precision photometry, aside from your tests. It'd be nice to look at an image where precision photometry has already been done, create an artificial satellite, and then remove it through your process and reprocess that photometry and see what happens to the errors from the original measurement. I completely understand that you've already tested it with the images you've had available, but I'd really love to see a little bit more photometric testing.
Yeah, definitely. I've been wanting to do more testing too, and that does sound like a good idea. I do have algorithms that I already have an algorithm that can automatically create an artificial satellite trail, so that would be interesting to test.
Okay, and we have a question from Gregory Sivkov. I've opened your mic. Whoops, I'm opening your microphone. You got your question for us, Greg?
Sure. I was going to ask Owen if you had possibly looked at something like Gaussian process regression as a way of speeding up your interpolation and your those types of things that you're most concerned about from the speed perspective.
Oh, sorry. Could you repeat? I heard something Gaussian, but I think it glitched out a second.
No worries. It's called Gaussian process regression.
Oh, interesting. I actually haven't heard of that. How does that work?
It's too difficult to go into detail here, but it's a standard machine learning way that is optimized for Gaussian processes, as its name suggests, and it's very good at doing interpolation and also giving you potential ways of thinking about what your errors of your interpolations would do to the process.
Oh, interesting. Thank you. I'll definitely check that out.
Let's see. Eric Dose has had his hand up. Eric? Can't seem to get you unmuted. You keep muting yourself back. There you go.
No, it was doing it automatically. Hi, Owen. I would be more interested in simply masking the pixels around the satellite trail. So my question is, how much of the computing time is simply in identifying the satellite trails so I can simply remove that path from my analysis altogether, rather than trying to do a photometric adjustment?
So right now, a fair amount of the time is spent on identifying the trail. I believe that can be significantly sped up. That is the thing I'm working on optimizing, that I would like to work on optimizing. But that is definitely, I think that it can be significantly sped up. The reason I've been experimenting a lot with removing it from the trail so that it will preserve photometry, because with increasing numbers of satellites, it'll become difficult to capture. Many other approaches will take several images and then sort of like with stacking and approaches such as that. But as more and more satellites go up, it'll become more and more difficult to capture all the enough images that don't have a satellite to apply the stacking approach.
Okay, at 400 images a night, I'm looking at more than 24 hours to analyze them according to this. So I would be out of business completely. It may be that some way to use synthetic tracking to collapse the star path using the graphics card. Might want to talk to Daniel about this problem.
Yeah, definitely. That is a good idea. I do think, yeah, there are several ways. I mean, there are definitely several ways to speed this up. I am still working on them. The algorithms I'm using can be optimized because I did not write them to be. I was just haven't worked on optimizing them yet, so they can definitely sped up that way. And also, they should be very easy to parallel process, so they should work they should go significantly faster on a GPU as well. Although I haven't tested that.
Very good, thank you.
Okay, I think I'm going to turn it back over to Jerry. I may have missed Jay Miller. If you could blink your hand at me, that might be good.
Joyce Guzik also has a question.
Okay.
On the panel. Joyce, I think you have to unmute yourself.
Yes, I had two questions. And I'm not an expert in this kind of photometry, but do you think that these trails could be removed if you were going to do some backyard astrophotography and deep exposures and still get all of the detail that's in an image?
Yeah, I believe so. I am. So the images I've been working with seem to. I've actually been working with two approaches. The photometry testing I've shown there, here is for like the first version of the code that I wrote, and I've been working on improving that. For example, with the wobble fitting is actually something that I have been dealing with in a second version of my code that I'm almost done with, and that one there is almost no, you almost can't tell that there was ever a satellite trail. There's very few, if any, artifacts in the image. So I think that could be used for astrophotography.
Good. The other question I had was about meteors versus satellite tracks. Are those different in shape or width or duration? And can you tell the difference in all photos? And does your algorithm work on both equally well?
I'm actually not sure how they would be different. I think I would guess that as long as the satellite trail, as long as the satellite in question is small enough that it appears as a point source, I would guess that they work similarly. I think that this could definitely be used to remove meteors as well, although I haven't tested that. And since they move a lot slower, I would right now my algorithm assumes that the satellite trail passes through the entire image, but it's very simple it would be a very simple fix to just apply it to only a small segment of the image that has the satellite trail passing through it.
Okay, thank you.
Yeah, thank you.
And Jerry, we have a question from John Hoot. So John, I'll go ahead and open your microphone up. You're going? Okay. Hi, John.
Okay. I was curious, does your algorithm work in the presence of multiple trails through an image, such as that bad day when your target happens to lie in the geosynchronous belt?
Yes, I actually have tested that on that, and it does seem to work. It does work with multiple images. I haven't actually run into an image with multiple real satellite trails, but I simulated a second satellite trail on an image that had one already, and it did work. So that should work.
Wayne, I have a question. What about a tumbling satellite that's varying in brightness as it goes through your field?
Yeah, so that's why I fit a polynomial brightness that varies, so that to take into account that the satellite trail might be varying in brightness along the image. In that case, it might be better to, if it's tumbling, it might have more of a periodic brightness. So it might be better to fit use a Fourier transform there. I'm still actually experimenting between whether to use a polynomial brightness or a Fourier transform for that. So that is something I'll think about. Thank you.
And then I have a sort of a final comment. I'm reminded of blockchain mining, and they look at their processing cards in terms of kilowatt hours of power it takes to process. And I wonder, between you and Daniel, I think that's maybe where astronomy might be going, is the amount of kilowatt hours it takes to process our images.
Yeah, that sounds like that could be what's happening.
Okay, so quickly, I guess if you're on the panel, you've unmuted yourself and asked questions. I've got one last question from Paul Makinen. So let me unmute your microphone, Paul.
Yeah, hello. I noticed that one of the first thing you do is do a plate solution to remove the stars. Now, what happens though if you have a photograph for which you can't get a plate solution? I mean, I've tried. I have one picture that for some reason ended up getting taken in. I used one of these remote telescopes, and for some reason it ended up in a field entirely different from where I was expecting it to be. And Astronometry.com or .net, whichever, I forget which it was unable to find a plate solution. So I'm just wondering, is there a solution in that case?
Yeah, I think that if there is no solution, the algorithm is actually pretty effective at finding the satellite trail, even when the stars are still there. It might still be able to find the satellite trail and remove it. It'll definitely be less. It'll probably be less accurate, but it should still be able to do it. Also, I think, yeah, I haven't actually run into an image that wasn't able to be plate solved yet. So hopefully those are rare, and so if they come across, they can just be thrown out if they happen to have a satellite trail in them and can't be plate solved.
Right. Well, fortunately, mine doesn't have a satellite trail. But anyway, thank you.
Okay, we have one additional comment from Eric Doe. So Eric, I'm opening your microphone, maybe.
Yes.
There you go, Eric.
So this is another reason to consider only masking out the trails, finding them and masking them out, rather than trying to remove every star and do an adjustment. Because when you have 10 or 12 tracks through a given image, which looks like where we're going to, all the current plate solving algorithms are going to have problems.
Yeah, that is interesting. Yeah, that could be. Yeah, I can see how that could be problematic. I think that still, if the FITS file has the location of that, if the FITS file has the location and orientation of the image without needing to plate solve it, then it could still run. Although yes, if I guess if there's a bunch of satellite trails, it could mess up astrometry.net. But as long as I'm only using astrometry.net to obtain to plate solve it. So if it's already known by, say, if it's a robotic telescope that knows where it's pointing accurately enough, it should still work.
Oh, and I'm gonna take John Hoot's question for myself. It looks to me like you're not really using the WCS solution from astrometry.net, just essentially the Spectrograph output from astrometry.net. Is that true?
Oh yeah, actually, I am using the WCS file.
Okay.
I just yeah, that was a simplification. Yeah, I'm taking the WCS file and then using AstroPy to feed that to convert between Gaia Gaia RA and DEC coordinates to pixel coordinates.
Okay. So, Jerry, why don't you take it away?
Well, I'm showing about 10 minutes after the hour. Why don't we get back here about 25 minutes after the hour, and we'll resume our second half of today's session.
Okay.
All right. Welcome back to our second half of the day 3 of the SAS Symposium. Next, we're going to hear from Rob Zellum. Let me get him on. Rob, you'll have to unmute your microphone.
Okay.
There we go. He's going to talk to us about Exoplanet Watch, a citizen science project to observe transiting exoplanets.
You should have control, Bob. There we go. All right. Thank you so much for having me, everyone. Really appreciate it. So as I'll be talking today about Exoplanet Watch. My name is Rob. I work at NASA's Jet Propulsion Laboratory, and I'm a giant space and NASA nerd, if you can tell by my NASA-themed Hawaiian shirt. So this is a citizen science project to observe transiting exoplanets, planets that periodically orbit around their host star, blocking out the star's light. So a transit measures the change in brightness as a planet passes in front of or behind its host star. So this animation here, we have a planet orbiting around the star. And if we're lucky along our line of sight, if the planet passes in front of the star, the planet will actually block out some of the star's light. And the amount of light that's blocked out directly tells us the ratio of the areas of the planet to the star. So by measuring the size and the dip in the light curve, we can actually directly measure the radius of these exoplanets. This method can also be used to study the atmospheres of these exoplanets. By observing when they pass in front of their stars, you can actually observe and measure how much light the atmosphere of the exoplanet absorbs or scatters the light of the host star. And by looking at the transits at a variety of wavelengths, we can then back out the chemical composition of these exoplanets and also measure things like their temperature. And this method has actually been used to discover 3,000. This is roughly 75% of the currently known exoplanets. This is a very, very powerful method that's been used to great success recently. So TESS is a mission that was launched a few years ago by NASA, and this is a dedicated space satellite that is to discovering transiting exoplanets. This is an all-sky survey, and it's predicted to find thousands and potentially up to 10,000 new transiting exoplanets. So today we know of about 3,000. TESS will then bring that number potentially up to 10,000. And the reason why it's really important, the work that TESS is doing, is because TESS is providing and will provide targets that can be used by future and current space satellites to observe and characterize their atmospheres. So for example, the Hubble Space Telescope at the top right has observed tens of planets, and it's used the transiting method to actually observe the atmospheric composition of these exoplanets. The James Webb Space Telescope will observe tens to hundreds of exoplanets. That's the satellite on the right in the middle there. It's an absolutely gigantic spacecraft. The golden mirror there is about 6 meters in diameter, and the bottom, the sun shield in purple right there, that's actually the size of a tennis court. It's truly amazingly big, and we're looking forward to its launch because James Webb will truly revolutionize translating exoplanet science, because it will take those observations that we've taken with Hubble and it'll get higher precision. Higher precision means you can look for smaller signals, but also James Webb will increase the wavelength coverage of these observations. Hubble's largely limited to one small size of spectral space, and James Webb will greatly increase that, allowing us to look for a bunch of new molecules. Ariel, this is a mission that will be launched by the European Space Agency, or ESA. This will be launching in about 2028. And this is a mission that's completely dedicated to observing and characterizing exoplanets. And Ariel's predicted to look at hundreds to thousands of exoplanets and actually characterize their atmospheres. And lastly, right now, there are 4 missions under consideration for the next generation of astronomy missions by NASA. So this is the Astro 2020 decadal review. And 3 out of 4 of these proposed missions will do transiting exoplanet science. So transits will continue to be a very important method that'll be used to look at the atmospheres of these exoplanets. However, if you want to observe an exoplanet and to characterize its atmosphere, you have to know exactly when that planet will transit in front of its host star. So for example, if I get time in the Hubble Space Telescope and I want to observe an exoplanet, I would look online and I would look up its transit time, and I would predict the next time that that planet would pass in front of its star. So I would maybe, for example, go on the NASA Exoplanet Archive, look up its transit time, its orbital period, and calculate its upcoming transit. And I might predict it to, for example, in this plot here, occur in the red dashed line. However, if those values have uncertainties on them, then that transit could actually become a little bit before or a little bit after than when I predict it to occur. So for example, if a transit has a 15-minute uncertainty, that means that's an extra 15 minutes that I need to include in my observation overhead to make sure that I observe that transit. Otherwise, I run the risk of missing that transit partially or even completely. And last time I checked, wasting time on large NASA missions is never a good thing to do. So we actually really need to keep these transit times fresh. And even timing on the order, uncertainty on the order of seconds is very important. So for example, for Ariel, let's say that there's maybe an uncertainty of about 5 minutes, 20 minutes on average of these exoplanets. Ariel wants to look at 1,000 exoplanets. So that starts to become a considerable amount of time that's basically wasted by trying to ensure that you observe these transiting exoplanets. But luckily, small telescopes are really the answer to keeping these transit times fresh. So a single 6-inch telescope is actually capable of high precision transit photometry. So on the right is actually a sample light curve taken by the Micro Observatory 6-inch telescope in Tucson, Arizona. And this is HAT P32b. This is a hot Jupiter orbiting a relatively dim star. So it's a Vmag of 11.2. Despite this target, slowing across the detector by over 300 pixels throughout the course of the night, despite it being a robotic telescope that's only 6 inches, it makes really beautiful observations and really high precision observations, as I'm showing there below. So really, small telescopes have the capability to measure these transits of these exoplanets, to update their mid-transit times, to keep their transit times fresh, to more efficiently enable the efficient use of large telescopes to follow them up and characterize their atmospheres. So what we've done in a paper that was recently accepted about a month or 2 ago is we looked at a bunch of data taken by the Micro Observatory and actually reduced by a bunch of citizen scientists and amateur astronomers. And we used that data set to sort of empirically estimate the capability, the power, the precision of these small telescopes to make transiting observations. And what we figured out is of the currently known 3,000 or so transiting exoplanets, a single 6-inch telescope can actually detect about 195 of them with high degree of significance, about 3 sigma. And then on the right, what I'm showing is so on the left, I'm showing the host star V magnitude on the x-axis, the transit depth on the y-axis, and then the color green is the detection significance, where a circle can be detected at least by 3 sigma, and a dark green is over 10 sigma detection. On the right, it's a similar plot, except we have period uncertainty and mid-transit uncertainty. So a small 6-inch telescope can really start to observe a large selection of these targets. And for example, there's a target on the right plot at the top that has a very high uncertainty in its mid-transit time and period. And that single 6-inch telescope can look at that one target, refine its mid-transit time, refine its ephemeris, and really enable additional science to be achieved with James Webb, with Hubble, or future missions. And small telescopes are really the answer. We figured this out from the micro-observatory data as well. So if we were to forecast the exoplanet targets that missions like James Webb, like Ariel, or an Astro 2020 decadal mission were to do, and look at their currently published mid-transit times and orbital periods and uncertainties on the NASA Exoplanet Archive, and then we simulated a single 6-inch observation by a single 6-inch telescope. And we calculated the time saved, as in how much better that single telescope could refine that mid-transit time, the upcoming ephemeris. And that's what we're showing here. This is the time saved by a single 6-inch telescope at the top row. And then if we expand that to a larger, but still modest collaboration of 16 6-inch telescopes in the bottom row. And you can see that a small array of telescopes, or even just a single telescope, could potentially save on the order of 10,000 days if these missions were to observe this roughly 200 to 500 planet sample. Those large jumps you might be seeing in the plots here below, those are actually on the left-hand column, those are actually planets with very large uncertainties listed on the NASA Exoplanet Archive. So for a little bit more conservative, we say, okay, let's say that James Webb is not going to observe these targets, and we remove them, we get the column on the right. But we still see that a single 6-inch telescope can still save a mission like James Webb on the order of 10 days. And on for the 16 6-inch collaboration or survey or network telescopes, you can save on the order of 100 days. So that might not seem like a lot, but for missions that are flagship NASA missions, where we want to use them as efficiently as possible to achieve as much science as possible, even small times like this really translate into a big impact on the mission and overall. Another thing we can do with multiple observations by small telescopes is we can look for things like transit timing variations, or TTVs. So if we have a multi-planet system where we have an inner planet and an outer planet, the gravity of the outer planet will actually perturb the inner planet. And as a result, it'll actually cause the mid-transit time to wobble back and forth. And by looking at this variation in the transit time, we can then infer the existence of a larger or smaller outer planet. And also it allows us to measure the masses of these planets by looking at their gravitational interactions with each other. Multiple observations with small telescopes also allow us to monitor for stellar variability. And we care about stellar variability because that actually directly impacts the measured transit depth. All of our observations are measuring how much light the planet blocks out on the star. But if the star changes in brightness from epoch to epoch, that transit depth actually can vary from epoch to epoch. So we actually need to monitor for stellar variability and then correct for it and remove it and characterize it as well. And this is very important for looking, for example, on small planets that are orbiting small stars, because small stars and dwarf stars are actually a lot more active than bigger main sequence stars. So this is definitely something that is of interest and necessary to characterize small planets such as Earth-sized planets that might be potentially habitable and orbiting around M-dwarf stars. Also, small telescopes have the opportunity to look for and characterize blended pairs. So on the right is a simulated TESS picture of a star field. So TESS, because it has such a wide field of view, because it wants to image a large swath of the sky in any given exposure, it also has a very large pixel size, in the sense that each pixel is very, very large if you project it on the sky. So for example, if we have an image of TESS on the right, TESS sees this object as one object and covering only one pixel of the detector plane. On the left is the true detector plane image from the microobservatory. And the microobservatory has a smaller, higher spatial resolution than TESS. It's about 5.21 arc seconds per pixel. And you can see that this one star is actually two stars. Now they look a little bit like potatoes, admittedly, because the tracking on the microobservatory isn't absolutely perfect, which is fine, but it allows us still to verify that that one star is actually a blended pair. It's actually two. And we care about blended pairs because that second star can actually dilute the size of our transit depth. So what TESS would see is, you might think that it's a Neptune-sized planet or an Earth-sized planet, because that second star causes the transit depth to go down a little bit. And then when we, if we were to do follow-up observations with things like the microobservatory and actually see that that's two stars instead of just one, we can then account for that dilution of the transit depth due to the additional light from the second star and actually verify and confirm that that planet is not as small as we thought. It's actually a Jupiter-sized planet. So this prevents us from making false detections of small planets. So all these ideas of all these impacts of small telescopes, even a 6-inch telescope, and we've done predictions for even 3-inch telescopes, can actually be very important and helpful for this effort as well. Really inspired us to launch a new program, a citizen science project called Exoplanet Watch. And this is a campaign aimed at citizen scientists to routinely observe high priority transiting exoplanets, planets that are likely to be observed by future and current missions, but planets that also have large uncertainties in their timing. And this effort would keep their mid-transit times and orbital periods precise. And this would be ensuring efficient use of these large telescopes. The data will be immediately public to the entire community, and observers will be listed as co-authors on any published results. So that's a very key thing. If you contribute to Exoplanet Watch, if your data or results are used in a publication, we will require the authors to include you as a co-author as well. You're doing the work, you obviously deserve the credit for that. And this program, this network of small telescopes operated by citizen scientists and amateur astronomers, will enable all those science cases I just discussed. And we're actually doing beta testing right now, and our official launch is somewhere in September, roughly, of this year. So I've been talking about all the science that it could enable, and actually Exoplanet Watch, even though we're in the beta test phase right now, has already enabled science. So we actually got a paper out of this already, published in PASP. So we have the usual suspects of professional astronomers here. Also, we have some of my summer interns, but also even in the first half of the paper, we had a bunch of citizen scientists, amateur astronomers that were pivotal and absolutely crucial to getting this paper published. Either they took the data or reduced the data, and without their help, this study would not have been possible. And just to call out these suspects right here, these are some of Calay's students, and Calais herself is on this as well. And they actually directly contributed to this paper as high school students, which was super impressive. And it's a pleasure to continue to work with them on this project. So Exoplanet Watch, what we do is we actually have our own website right now that's in a beta test as well. Just Google NASA Exoplanet Watch. And we're already identifying high interest targets every night for each of the US time zones. So you can actually go on there, look at a priority target, and actually observe it potentially tonight if it's clear in your neck of the woods. Then you can observe those targets or any other transiting exoplanet with your own telescope, or if you can get time on a robotic telescope, such as the microobservatory or LCO, you can use that as well. Then you actually reduce and model your own data. You can use your own favorite reduction code like AIJ, or you can use our own official pipeline called Exotic. Then you upload your data to the AVSO's exoplanet database. We're very lucky in that we have this awesome collaboration with the AAVSO, and they're allowing us to use their exoplanet database for our users to host their data. Then we automatically scrape this data, we perform all of our analyses, and make our results immediately public to the entire community. So I mentioned Exotic. This is our data interpretation code. It takes raw FITS files and fully reduces them using multi-object photometry, and it also fits your light curves. So then this is actually what produced the transit I showed you earlier on the bottom right. Exotic also has a really cool feature where it does real-time reduction. So at the top right is demonstrating this feature. So let's pretend you're at a star party and you want to observe a transit. Observing it by eye is pretty boring because you're looking at a star dim very subtly over the course of the night. But if you use the real-time reduction software, you can actually show people on your computer screen, hey, we're observing an exoplanet cast its shadow on the Earth in real time. And that's available at the GitHub link at the bottom. It's also linked from our website as well. So we need you guys right now to help us with observing any exoplanet and uploading your results to the AVSO exoplanet database. If you don't have any data, that's actually not a problem at all. There are many different ways you can get data from robotic telescopes like the LCO or micro-observatory. And we need you to help test the exotic reduction code. If you go to the GitHub link or our website, you can download exotic. It comes with a sample data that you can actually reduce. So once you install exotic, you can go from beginning of raw FITS files to a fully modeled and measured transit light curve in about an hour on your own laptop. Again, we're launching in September of this year. And if you want to get involved at all, or if you have questions at all, just feel free to contact me at rzellum@jpl.nasa.gov. That's my last slide. Yes. So thank you so much, and I'll take any questions.
Thank you, Rob. Do we have some questions, Wayne?
Well, we have a few questions. Tom Palakas pointed out that I think one of the references was to a site that was behind a paywall where the archived version of that paper was readily available. So that was something that I thought I might bring up. Kaylee Talk has got a question as well. Kaylee, I'm going to go ahead and open your microphone. Hi, Kaylee, are you there?
Oh yeah, I'm here. I thought you were just going to read it. Thanks so much, Rob, for the awesome talk and the nice shout out. I was just wondering whether it was, if the goal is to save time on upcoming missions, would it be most useful to like focus on a single target or jump around and look at as many targets as possible from the high priority list?
Ooh, that's a great question. It depends on what these telescopes will be observing. So since I don't necessarily know what is being proposed to be observed on James Webb, for example, that's why we identified this target list. The target list is actually drawn from the targets we think that are most likely to be observed by missions like James Webb. However, in the future, what I'll be doing is once we're a little bit more established is I'm going to let the exoplanet community know that if they have a high priority target that they want us to focus on, we can send an alert to our users or on our website to focus in on that one target and to refine its ephemeris. Also, you don't have to observe any of the targets we identify on our website. You can observe any target you want. So if you wanted to observe a planet like HD 209458b, that's a really well characterized planet with a very precise ephemeris, go for it. Really just trying to get as many people as involved as possible on this. And thank you for your work and all your awesome students. I really couldn't be doing this without your help. So thank you, Calais.
Thanks so much.
Okay, John Hoot has his hand up, so let's go ahead and open John's microphone, if I can. I can't seem to get it open. Up there, up. There we go. Hi, John.
Hi, I was curious what the system requirements were for running Exotic. What is the OS or processor requirements?
So let's see. I run it on my Mac pretty well. It runs on other people's Windows laptops. I think we also have it on Linux. So we have installation instructions for all of them. really it's just going to run more slowly on your own computer if it happens to be older. However, to plug Calais and Quinn Perriam, one of her students, Quinn actually figured out a way of running Exotic in the Google Cloud, so and then the Colab function, I believe. So if your computer cannot handle running Exotic, or you find it running too long, or you just don't want to run on your own PC, that's fine. You can actually run it in the cloud. And I think Calais has some awesome instructions written up on how to do that. And Quinn's made it pretty user-friendly as well.
Does it perform, how does it perform versus the Astro Image J plugin?
So I think Quinn and Sujay did a head-to-head comparison of Exotic versus AIJ, and I think Exotic got higher precision light curves. If I remember correctly, another pro of Exotic over AIJ is that it actually does the light curve modeling as well. So it actually runs a Markov chain Monte Carlo method that does a full fitting of the mid-transit time and the orbital period. So that's that line that you see in this figure right here in red. So that red line is actually a fit by Exotic to the data. So it does the additional extra step beyond the multi-object photometry. Exotic also will optimize by picking the correct comp star that minimizes the scatter in your data. It also does a variable aperture size as well. And that's mostly automated. The user does interact with the code in the very beginning, but then after the first few minutes to seconds sometimes of interacting with the code is largely autonomous, so you can actually go to sleep, you know, after your observing night.
Thank you.
Mm-hmm. And also a quick note about the paywall thing. So yes, the official paper is behind the past paywall, but the archive version is basically identical, so you're not missing out by getting the free archive version on ADS.
Good to know. We have Brad has his question poised here. Brad, I'm going to go ahead and open your microphone, if it'll let me. You might be muted at your end.
Now we're unmuted.
There we go.
Could have read that one. For citizen science, are you looking for transit time variations only, or are you also interested in filtered data?
Filtered data, and what do you mean? By using different photometric filters, or?
Yes, indeed. Yeah, any color variation.
We don't really care, honestly. You can use whatever filter you want. Since the timing is filter independent, it doesn't matter. So whatever you can get, that's great. When you upload your data to the AAVSO exoplanet database, you do indicate what filter you're using. So in the future, if we identify a science case for analyzing multiple filters of data, for example, if we wanted to build up a photometric spectrum of these exoplanets, we could do that in the future. So yeah, also all these data products that we're making will be available for any of you or the professional exoplanet community to use for future studies. So if someone figures out they can use Exoplanet Watch database or data products for a really cool new study, they're more than welcome to do so. But again, they'll be required to include US co-authors and also to send a shout out to the Exoplanet Watch team.
Okay, we have John Murrell has his hand up. Let's see if we can get you unmuted. There we go. Hi, John.
Hi, good evening. 2 points really. One, I don't know if you're aware, there's a similar program already running over here in the UK, doing virtually the same thing. So I hope you're actually sort of tying up on what the list of targets are, but obviously the time difference between here and there will mean different things could be searched for. The other thing is I've said to other people is that, of course, the Gaia data will be coming out sometime, the photometry data, and that will give you 4 or 5 years of timing backwards from whenever the release date is. And of course, your transits will have to meet that. And if they meet or fit the Gaia data, of course, you get quite accurate timing out of that eventually.
Yeah,
so that, I haven't heard anyone consider that, but it's something that someone needs to look at.
Yeah, and there's nothing stopping anyone from using Exotic, for example, on the Gaia data. So it should work as long as the image headers, I've set them up properly in the code. So that would be really a cool test to do. So if someone such as yourself is interested in grabbing the Gaia data and using Exotic to reduce and measure these transit times, please let me know if it doesn't work with it so I can fix the code on that. And regards to the other efforts, oh, go ahead, sorry.
I was going to say a lot of the data isn't available yet because it was due towards the end of this year. The Gaia photometry data has been antivirus or whatever the proper statement is. So they're talking about sometime next year now for the initial 17 billion, no, 1.7 billion light curves, I think, just to keep people busy.
Yeah, exactly. Have to hire a lot of interns to do that. And then regards to the other efforts, yeah, there's, for example, the ExoClock project. That's actually a European-based project that is run by the Ariel space mission to actually help out Ariel. And I should have mentioned on here, my apologies, that we're actually collaborating with them as well. So we've agreed to collaborate with each other, and we're actually thinking of ways in the future to sort of do transit handoffs. So for example, if a transit starts in Europe, but it doesn't complete until after it's set in Europe, you can potentially pick up the second half in the US. Alternatively, you can have multiple people across the world observing the same target if the timing permits. And we're planning on sharing data products, and helping each other out with identifying targets as well. So yeah, luckily I'm friends with a few of those people at the ExoClock. I just had a telecom about a few weeks ago. So really excited to be working with them more in the future.
The challenge might be, of course, those in the deep south that are not visible from Europe or quite a lot of the states. So I don't know whether you can actually, you need to get the Australians, New Zealanders and others involved.
Yeah. And so we're talking with Michael Fitzgerald, for example, in Arizona, good Lord, Australia. And there's nothing stopping anyone from going on, for example, the Swarthmore Transit Finder website to see what's available any given night and invisible, observing those targets and then throwing them on the AAVSO database. So anything that's thrown up on there will be scraped by the ExoWatch project. And I would love people, for example, in the Southern Hemisphere to get involved in this project. That'd be awesome.
Okay, thanks.
Thank you.
Okay, thanks, John. Next on the list is Pat Boyce. We haven't heard from Pat yet. Let me start your microphone, Pat. Hi, Pat. How are you doing?
I'm doing fine. I only had a comment, and I just want to be sure that people know that Rob has designed this code such that when it completes, it formats your report to go directly to AAVSO's database, and so it can be quite straightforward to really populate the database and make this program work. That's all.
No, thanks, Pat. That's a great point. So we really tried to make it as easy for users to start with their raw FITS files and have all the products they need to upload directly to the AAVSO database. So it's the text file that you need to upload, as well as the image of the field of view with the labels of what the target and comparison star and your relative aperture sizes are as well. So it's really trying to be that one-stop shop for exoplanet observations and reductions.
Okay, we have a question from Sebastian. Sebastian, let me open your microphone up. Hi, Sebastian. How are you?
Hi, fine, thanks. Can you hear me?
Yes.
Great. Hi, Bob. Thanks for your talk. Are the exoplanet elements in the NASA Exoplanet Archive being updated in real time as new results are published? And if not, where can we get the most up-to-date elements?
That's a great question. They're supposed to be, but with so many targets, it's difficult, I think, for them to get the most up-to-date values. I believe the Swarthmore website does pull from the Exoplanet Archive. There's other efforts around the world as well, such as the ETD, the Exoplanet Transiting Database, run by the Czech Astronomical Club. They have a really excellent transit timing database as well that are also updated by amateur astronomers. That's actually the group that ExoClock is working with. So just like we're working with AVSO, ExoClock is working with ETD out of the Czech Republic. So it's a great question. The best way to find the most up-to-date values is to check for the latest publication on that with the newest, most recent data. Typically, I found that the Exoplanet Archive has gotten a lot better about keeping those values up to date.
Okay, thanks.
But it's not a guarantee. So perhaps it'll be us in the future that has the most up-to-date values. I hope that's the case.
Yeah. Okay, thanks.
Thank you.
Okay, it looks like that just about takes care of it, if I'm not mistaken.
All right.
Wayne, Stella had a question. I don't know if it was answered or not. Stella, are you still there?
Yes, I am. Hi, Rob. Really cool project, and we're really very happy to be part of it. Quick question, could you please clarify whether the target list is going to be available through the AAVSO targets tool, or it's going to be a separate list? How are you going to disseminate that information?
So it's actually being published right now daily on our website. So every morning at 4 a.m. Pacific time, we update all those targets. So we have identified a priority target for each of the US time zones, but I would love to coordinate with you guys with also getting that on the AAVSO target list. So we should definitely talk about this in the future with Dennis and everyone else. That'd be great.
Yes, and the follow-up question, how many targets do you have right now?
Oh man, it's a weighting function. So it actually takes into account all the currently known exoplanets and it weights them to prioritize targets that are big and bright. And these big bright targets are likely to be followed up by missions like James Webb. But it also has a weighting function that also weights by the uncertainty on the next transit. So these are targets that are going to be followed up by James Webb. These are targets that can also be observed with a small telescope. These are targets that have large uncertainties. So technically it's all 3,000 exoplanets, but those are probably not the ones that, you're probably not going to get the dim ones as well. So we tried to identify on the website the VMAG, I believe, and if not, I need to have that added to the website to sort of identify to the user to if they can actually hit that target or not.
Very nice. So at some point we can work together to identify a prioritized list for our observers so they can focus on it. Excellent. All right, we'll keep talking. Thank you so much, Rob.
Stella. Appreciate it.
Okay, I think we probably time to move on now. Rob, thank you very much for this, and I'm sure all the links that we need are in the publication. Oops, he's gone. Okay.
Okay.
Next, we're going to hear from Joyce Guzak, and she's going to talk to us about data analysis of bright main sequence A and B type stars. And that's a different title than it's up right now.
What? Oh.
I shortened the title slightly because it was so long. I didn't want to take up all the real estate on this view graph. So thank you for joining me. I'd like to also acknowledge my collaborators, co-authors from New Mexico, Poland, and Italy in this case, many who have all helped me with this presentation. So I am trying to see if I can find the place where I can advance my slides. I'm not sure. I'm not seeing the little arrow in the lower left like I did before.
Click on it.
Click on it. Click on the lower left and it'll appear.
Here.
Okay, I almost saw it. There it is. So if I just click like that one. Yeah. Okay. All right. So I'd like to start by telling you a little bit more about pulsating variable stars across the H-chart diagram and then zooming in on the ones that we're going to be seeing some light curves of today. So during my lifetime, we've learned about many different new variable star types, and stars in almost every evolutionary state can be found to pulsate. So on this picture, you'll see the main sequence variable stars that we're going to focus on today, and in particular the Gamma Doradus variables and the Delta Scuti stars, which are just a little bit more massive than the solar-like stars, and our sun is down here in this picture. So there are also pulsating red giant stars, the classical pulsating Cepheid variable stars, and there are even pulsating white dwarf stars here on this white dwarf evolution sequence. Yes, okay. So this is a little bit of a closer look at the main sequence where you can see the solar-like stars down here, the Gamma Dor, the Delta Scuti, the slowly pulsating B stars, and the Beta Cephei variables, which we will talk about later. So the Gamma Dor and Delta Scuti stars are burning hydrogen into helium in their cores. That's what it means to be on the main sequence. And they also pulsate not just in one mode, but in many modes simultaneously, both radial and non-radial modes. So the Delta Scuti stars are about twice the mass of the sun, and their pulsation modes are pressure or acoustic or sound modes, and they have periods of around 2 hours. The Gamma Dora stars are about 1.5 times the mass of the sun. They're down here, and they pulsate in gravity modes, where gravity is the restoring force, like waves on the ocean, with periods of 1 to 3 days, so longer periods. So the stars on the main sequence have different internal structure, and the pulsation modes can tell us about what's going on inside the star. So for the sun has a radiative core. It has photons working their way out, bouncing off the atoms and the electrons in the core. And then it reaches, the radiation reaches the outer layers of the sun, where convection, or basically boiling motion, is causing the energy to get out. So the sun and stars a little bit more massive than the sun, like the Gamma Dora stars, have convective envelopes and radiative cores. So very small, low mass stars are almost fully convective. And the Delta Scuti stars and stars more massive, like those Beta Cephei and SPB stars, have a convective core because they're burning hydrogen into helium very quickly, and the energy just can't get out fast enough by radiation, and convection is carrying the energy. But they have radiation, for the most part, carrying the energy on the way out of the envelope. So they have different structures. So the reason that stars pulsate, one of the reasons is the so-called kappa, or opacity effect, inside stars. So this is a picture of opacity versus temperature in the inside of a star, with the center of the star toward the left and the surface on the right. So for a star where radiation is carrying the energy out in that layer, if the opacity or the resistance to radiation transport gets higher, that area can block the radiation and cause that layer to be pushed out, and then it pushes out and it cools, and then it comes back down again, and that's what causes the pulsation driving. So for Delta Scuti star, it's actually this layer right here at about 50,000 degrees, where the second electron of helium is ionizing, that produces this bump, and that's the region that's in just the right place in the star for this mechanism to cause the Delta Scuti pulsations. For the more massive stars, the Beta Cephei and SPB, it's more this Z bump, or this area where iron and elements around it are ionizing, that's blocking radiation and causing the pulsations. So before the Kepler spacecraft, I'll maybe allude more to Kepler later. It was launched in 2009, and it lasted until 2018. It was looking for transits of planets to try to find planets around stars, just like in the talk we just heard. Before that spacecraft, we had many observations of Gamma Dora and Delta Scuti stars discovered, and they pretty much were in the region of the, this is a log G, but you can also think about it as, you could translate it into luminosity if you wanted to, log a surface gravity and effective temperature. They lay in the instability, pulsation instability regions where we expected. All the Delta Scuti stars in the red were pretty much between this place called the red edge and the blue edge of the instability strip, where our theory said they should be. And the Gamma Dora stars, which are really, the pulsation is driven more by convection, a process at the bottom of the convection zone called convective blocking, those gravity modes, and they should lie between this line and this line. And they pretty much do. There's some a little bit on the outside of this theoretical Gamma Dora instability region. There are a few hybrid stars, and these are stars that pulsate in both types of modes, and you might expect them to be in the overlapping region between the two instability regions, the red area Delta Scuti stars and this area here, the Gamma Dora stars. And for the most part, before Kepler, the hybrids that showed both types lay in the right region. Let's see if I can advance. Okay, so then in 2010, we took a look at the first data from the Kepler spacecraft, and many more Delta Scuti and Gamma Dor stars and hybrids were found. And we found that there were hybrid stars, which are the black ones that pulsate in both Delta Scuti P modes and Gamma Dor G modes. They were all over the instability strip. They weren't actually of both types. They weren't found in just this overlapping region like we expected. We also found Delta Scuti stars to the red or to the blue of the theoretical lines, and also Gamma Dor stars, the blue asterisks here, way outside of their instability regions. So some of this might be inaccuracies in the surface gravity or the temperature measurement. You can see the error bars up here, but even when those are refined, this problem persisted. Our theory no longer explained these stars. So recently, after Kepler finished its mission at the end of November of 2018, the TESS spacecraft, which you just heard about in the previous talk, was launched in April 18th, and its main mission was to search for transiting exoplanets around GK and M stars. But it is continuously viewing individual targets for about 27 days, which is called a sector. And if these sectors overlap, I'll show you this in a second, you can actually look at a particular star for up to a year with the TESS spacecraft before it has been moving to the other hemisphere to look at another part of the sky. And they have a guest investigator program, which I've been applying for data from to get data on variable stars, and I've been requesting 2-minute cadence light curves. So the TESS spacecraft is collecting data integrating over 2 minutes and saving that point and then sending it down to Earth, and they put it on the Mikulski archive, and I can download the light curve and analyze the data. So TESS is in an elliptical orbit in lunar resonance around the Earth. So it is not orbiting the Earth, it's actually in this elliptical orbit outside the Earth-Moon plane, and it flies by the Moon every 13.7 days and gets a little nudge to stay in resonance in that position. And then it can look out at a direction of the sky for 27 days in the case that they have it programmed now. And what's nice about this is you don't have the Earth shadow blocking any observations over a day, so it can observe continuously, just like the Kepler spacecraft that was in an Earth trailing orbit could do. So this is a map of the TESS photometer frames. They have 4 frames lined up in a strip here that covers the sky from the ecliptic pole to the equator, near the equator, not quite all the way down. So this is ecliptic coordinates, and it looks at one of these strips for 27 days, and then it moves to the next strip and the next strip. So TESS started with the southern, I believe it started with the southern hemisphere, and then it moved to the northern hemisphere. So there were 13 strips in the southern ecliptic, below the southern ecliptic plane, and then there are in process observations of 13 strips called sectors above the ecliptic plane. So where these strips intersect or overlap, stars in these regions may be observed for more than one 27-day period. So stars in the yellow could be observed for 54 days, and the blue 81 days, and stars here near the ecliptic pole for almost an entire year. So the last guest investigator program that we proposed was to look at a type of A star. So these are stars about the mass of a Delta Scuti star. A Delta Scuti star is an A-type star usually, but they showed peculiar abundances called metallic line A stars. And they show underabundances of calcium and scandium and enhanced abundances of titanium and iron group elements on their surface in spectra. And these abundance anomalies are thought to be caused by radiative levitation and diffusive settling of elements in the envelope of the star. This diffusive settling is also expected to affect the helium in the envelope and cause it to settle out of the pulsation driving region. So stars that show these strange abundances are also not expected to pulsate because the helium layer that's driving the pulsations has settled out, and you're not getting that bump in the opacity to block the radiation. So we're trying to see if stars really behave this way. Gianni Catanzaro in Italy in 2019 did a survey using spectroscopy and Gaia parallaxes to determine the stellar parameters and abundances for 62 metallic line A stars, and then he put them on the instability strip regions and showed that many of them are in the Delta Scuti or the hybrid instability region. So they might be expected to pulsate if this diffusive settling wasn't happening or was happening less efficiently. So our goal is to use the test data to determine whether those stars actually pulsate. So this is the picture from Catanzaro's paper, and all of the 62 stars he observed are here, and many of them you see are in this Delta Scuti instability region, and some of them are in this overlapping region between the Gamma Dor, between the two green lines here, and the Delta Scuti region, this hybrid pulsation region. Some of them are completely outside. So maybe these would be expected to pulsate in Delta Scuti modes. So our questions are, why do some stars in those regions pulsate and others do not? That's actually something that we've seen that was known before this project. How is the chemical peculiarity connected to the pulsations, and are new pulsation driving mechanisms needed to understand these stars? So after, I think we've done 21 out of 26 now, but other sectors 14 to 26 is looking at the Northern Hemisphere from the test data. And we have 21 sectors of data now available. And is that right? Yeah, I think it's 21. It's 21 sectors and 21 stars that we looked at out of Catanzaro's 62 stars total. So these are the 21 metallic line AM stars we've looked at so far. And all the ones without a symbol next to them are constant. They actually didn't show any pulsations at all. So there were a couple though, this one that showed Delta Scuti pulsations, which is okay because that's right in the instability region for Delta Scuti stars. There was two hybrid stars that showed both kinds. You would expect those to be right in here. Well, this one is far away from the hybrid star region. So what is it doing over there, pulsating in both types of modes? And then we have 3 Gamma Dor stars, which should be over here, but are so hot you wouldn't expect them to be Gamma Dor stars. So we have lots of questions for pulsation modelers and theorists to try to figure out. So next I'd like to show you some of the test light curves and the Fourier transform that gives the amplitude spectrum and the pulsation frequencies for the stars. So this is one of the Delta Scuti stars, a low amplitude Delta Scuti star. So this is 2 sectors of test data. So this is 2 27-day observations. So there's a few places there are gaps. And this is a 3-day zoom in. So even if you zoom in, the star is pulsating in many modes simultaneously, and the period is only it's 5 or 10 cycles per day, so a few hours. So you see many pulsation modes. It's hard to make sense of that without doing a Fourier transform. But when you do a Fourier transform, you see that this star has quite a few pulsation modes, different frequencies between about 5 and 15 cycles per day, or if you want to work in microhertz, down here about 100 microhertz. This is a Gamma Dor Delta Scuti hybrid star. So this is a picture of the sector 3 light curve for this star, and this is a zoom in, so it's got some longer period pulsations, but also some shorter period things going on. And here is the Fourier transform showing the amplitude spectrum. You can see there are several periods here, around 1 cycle per day. These are like the Gamma Dor pulsation, typical for Gamma Dor pulsations. And then there's a lot of frequencies here in the Delta Scuti pulsation mode range. So it's a hybrid, has both. See, I just showed you that one. This is another hybrid. Same thing, a lot of Delta Scuti frequencies and a couple of Gamma Dor frequencies. I'm calling these candidates whenever they're Gamma Dor because sometimes these low frequencies, they may not be a pulsation mode. They may be rotation causing activity or and star spots causing activity that makes the light curve go up and down with a period that's typical of a Gamma Dor star. So more work is needed to know if it's really a pulsation mode or a just a rotation or a star spot changing size. So in addition to those hybrids and Delta Scuti stars, there were 3 more Gamma Dor candidates, and these were all too hot to be Gamma Dor stars according to the theory, but you see periods down here in the 1 cycle per day or 2 or 3 cycle per day range, which are typical of Gamma Dor stars. So these are why they're called Gamma Dor candidates. Whoops, I think I went too fast. Okay, back up. So one of the stars that we looked at was actually an eclipsing binary. And so you see the binary eclipses, the stellar eclipses here between when one star goes in front of the other and then goes back behind the other. So it's really hard to see any pulsations in this. They would be buried in this light curve. But it turned out that another group had looked at the star with Kepler data and had removed the light curve, the binary light curve, and they were able to see that there actually are Gamma Dor pulsations in one of the components of this star. And then there were several stars that didn't show more than 1 or 2 frequencies. They were mostly in the Gamma Dor range. They had pretty high amplitudes, several parts per thousand. This one is 6 parts and 4 parts per thousand, periods of many days. And I don't know what these are. These could be slowly rotating stars, rotating once every few days with star spots. These could be close binary ellipsoidal variables, or this actually could be a pulsation. So more work is going to be needed to understand these stars. So this is a summary of the test part of the talk. Of the 21 stars that we observed out of that Catanzaro 62 star sample so far, we found Catanzaro predicted a lot of Delta Scuti stars could be there, 1 hybrid and a few constant stars. But we found 1 Delta Scuti, 2 hybrids, 3 Gamma Dor candidates, an eclipsing binary, and 9 constant stars, and about 6 stars that we don't know why they're varying. So more work is needed, follow-up work by ground-based observers, perhaps, to figure this out. I should point out that all of these stars are 8th magnitude or brighter, so they should be accessible by amateur observers easily. So the next thing I'd like to talk about is the bright constellation satellites. These were launched in 2013 to 2014 by a group, a consortium of Austria, Canada, and Poland. And they were targeting very bright stars, magnitude 6 or brighter. There were 6 satellites launched, 3 red filter and 3 blue filter, but the bright Montreal number 6 didn't get off the upper rocket stage, so there's only 5 satellites in operation. So they're in low Earth orbit between 600 and 800 kilometers. They observe for up to 180 days for at least 15 minutes during each orbit. And so they do have a lot of downtime as they go around the Earth. And the properties of the time series are constrained by the camera exposure for the bright stars and are 1 to 5 second integration time, and they're collected about 3 to 4 times per minute for 15 to 35 minutes per orbit. So for these, I'm going to bring in the beta Cephei and the SPB, slowly pulsating B-type stars. So above the Gamma Dor and Delta Scuti instability region, there's a set of gravity mode pulsators, the slowly pulsating B stars. that are about 3 to 9 times the mass of the sun. And they also pulsate in those low frequency, one or 2 or 3 cycles per day periods. And the beta Cephei stars have pressure modes, just like the Delta Scuti stars. So they kind of parallel this set with masses 7 to 20 times the mass of the sun and periods of several hours. So for the bright, they also have a guest observer program where you can propose observations. So we proposed observations of 4 stars in the Kepler field of view, which I'll show you later, which Kepler really tried to avoid bright stars because they would saturate the pixels. So we only observed with Kepler a few bright stars directly to get light curves for them. But I wanted to try to see if some of these other bright stars in the Kepler field showed pulsations. So we looked at HR 7591, which is a little bit more evolved B-type star, magnitude 5.89, and there were spectroscopic line profile variations that said it might be a beta Cephei variable. And this is HR 7179. It is magnitude a little bit fainter than 6th. It's right in the middle of the main sequence, another candidate beta Cephei variable from prior observations. These two had prior TESS and Kepler data. And this B-type star, HR 7403, is a B emission star, which is very strange. It's probably a young star. It's rotating pretty rapidly. It actually has a disk around the equator called a decretion disk, which means that they think that this disk was formed by material thrown off the equator of the star. So it might have been rotating rapidly and probably pulsating too. And this material came off the equator and has formed a disk around the star. And we only have bright data unless you work hard on the Kepler data to try to get something out of it, which some people have. And then there was a 4-star, an A-type star that we had observed with Kepler, again, magnitude 6. So it took an extraordinary amount of effort to get the Kepler 2-minute light curve, but I wanted to follow up with it with the bright satellites to see if we could get some more information. This star may have an unusual pulsation driving mechanism, so it is a lot of interest.
Joyce, we're going to have to finish up in just a minute or two.
Okay, thank you. All right, I'll probably just quickly skip through these then, and you can read my paper for more about the Kepler data. But I wanted to point out the Kepler field of view had these CCD arrays, and you see that the bright stars were avoided them. They're between the CCD pixels with the exception of theta sig. So that's why it's nice to have the bright data so we can look at brighter stars. So this is a look at the first of the B-type stars with Kepler data. You see it has a pulsation, an SPB-like pulsation, but Bright wasn't able to detect it. Kepler had much better photometry than Bright does, so it didn't work to find that frequency. For the second B-type star, TESS was able to find a lot of SPB-like pulsations, low frequency pulsations, and Bright was easily able to see those pulsations. You see the frequencies here with a few more even at a little bit higher frequency. So there's a lot of promise to follow up with that with the Bright spacecraft. And the third star, this is Bright data. We were able to find a frequency at 1 cycle per day and about 2 cycles per day. And you might think that's a spacecraft artifact, but Pope et al. Looked at the Kepler data and extracted from the pixels a light curve and were able to find those same 2 frequencies. So I don't think it's an artifact. And this last one turned out to have, have too low high noise level to find anything. And I'm excited about this last, this last star, this A star. It has a lot of very low frequency delta Scuti, low amplitude delta Scuti-like pulsations. So I think this is going to be a really good one for astroseismology. Okay, so these are my summary of the Bright data. A lot of future work to follow up to figure out what these stars are really doing. There are some more data that we could try to extract from the Kepler and TESS full frame images in order to reconstruct a light curve and see if we can get more out of that. And we need all these constraints for stellar modeling to solve our problems, because we don't know why these stars are pulsating and what's going on inside. Okay, thank you.
Thank you, Joyce. I think we're going to have to hold questions for perhaps after the session.
Okay.
We're a little over time. Thank you, Joyce. Next, we're going to hear from Cindy Wang and Sahana Datar, and they're going to talk to us about comparing the ages of NGC 1513 and NGC 2420. Let me get them on. Very good.
You have control, Cindy.
Okay.
Click it.
Hi. So we were trying to compare the ages of two star clusters, NGC 1513 and NGC 2420. So those are pictures of our star clusters, NGC 2420 on the left and NGC 1513 on the right. So we had to request the images in the blue filter and the visual filter from the Las Cumbres Observatory. And we created a color magnitude diagram to approximate the age of the star cluster. And we used the brightest stars in the star cluster because they had the shortest lifespan. So we knew that the star cluster would be at least as old as the brightest star. So for our procedure, we found the magnitudes of the stars from the APAS catalog, along with the images we requested by opening them up in Astronomy. And we did this by clicking on the stars in AIJ, and then it would open up the magnitudes of the stars in the Simbad catalog. And we found the BNV magnitudes for each of the stars in the images. And then we corrected for reddening, which is like background dust for each of the stars. And then we used one star from each of the star clusters to estimate the age of each cluster. And we decided to use the bluest star because it has the shortest lifespan since it burns the fastest. And then we use that to estimate the age. So we used the B minus V value on the x-axis as a proxy for temperature, and the visual magnitude on the y-axis is a proxy for luminosity, because those are the axes on the HR diagram which we compared our color magnitude diagrams to. And so we concluded that these stars in NGC 1513 contained mostly hot stars that were around 10 million years old, and NGC 2420 contained mostly cooler and dimmer stars around 100 million years old. So for future work, we found out that NGC 1513 has a higher proportion of hotter stars compared to NGC 2420. So something we would like to look forward to researching in the future is how the size of a star cluster affects the stellar population. Yeah, thank you.
Thank you very much. Do we have a question or two? Wayne?
Sorry, I was muted. I don't see any raised hands. I don't see any really outstanding questions. So.
Okay. Well, thank you very much.
Thank you.
Next, we're going to hear from Brian Kudnick, the Prairie View Observatory. Get you on, Brian.
This has been a work that's actually been in process for over 20 years. I first started working at Prairie View A&M University, which is a historically black college that's part of the Texas A&M system. We're located just outside of Houston, Texas, actually about an hour's drive west-northwest of Houston, Texas. I started with the Prairie View Solar Observatory and worked there for several years. And the new observatory is a recent addition. You can actually see you can actually hear about the full story about how the recent addition came about by going to my talk for the Houston Astronomical Society. I gave a talk at more length about the Prairie View Observatory for their June meeting. So you can go to astronomyhouston.org to get more story about the construction of the observatory and the story behind how it came to be. So what I'm going to focus on for this presentation is the first light aspect of it. The observatory, first of all, consists of 3 domes in 2 buildings. We have the classic Prairie View Solar Observatory, which was built back in 1997, and I started working on that with that program from 99 to 2001, and then I transferred to the physics department and worked with them. I'm actually still with the physics department. We acquired complete control of the observatory in 2016, and the decision was made to add the additional structure. Since the solar observatory is primarily concerned with observing the sun, we wanted to add some nighttime observing capability. By the way, the solar observatory edition also has it's going to have 2 domes. Well, actually, it has 2 domes, and it also has a visitor center where we can receive up to 50 visitors. There's a couple of control and work rooms, and we have what's called a Flux calibration laboratory. That's a work that's going to be developed at some point in the near future. So the telescope features 2 piers that have a very low vibration tolerance of about 0.485 arc seconds, and so they're very stiff, very good for high resolution imaging. The instrument that we see here is a plane wave 24-inch CDK telescope, and that's going to be our primary instrument. We have the S-Big camera hooked up at the end. So we're currently in the process of getting the bugs worked out of this particular system because there's some issues with balance, coordinating the dome with the telescope pointing and so forth, but that's something that we hope to work on over the summer. The East Dome actually has a Meade 16-inch that I've been using more regularly, and I'll talk more about that in just a few minutes. One of the primary components of our observatory is outreach, and so what we plan to do is we plan to make the observatory available to interested groups. Not only are we going to be working with our own students, we've already used the observatory and some of the images that we've produced by the observatory in our physical science labs and classes. I incorporate some of this in my own classes that I teach on campus. Last year we had 40 elementary school girls and their teachers come visit us on what is called a day of science, and so we were able to show them the telescope and everything. And so we have large monitors in the visitor center that are going to be hooked up to the 2 telescopes and the 2 domes of the addition, and we plan to have video connected to those telescopes that can port to the monitors and show the public what the telescopes are viewing in real time. In addition, we have many ground-based telescopes that we can wheel out fairly easily and provide a more classical star party situation where people want to look directly through telescopes. So we did start a solar observation program, which actually was put on hold in mid-March because of the coronavirus outbreak, but I do plan to get back to the observing program tomorrow, as a matter of fact. This actually mirrors what we did with the solar observatory back in the late 90s, early 2000s. Primarily, we're working in hydrogen alpha. We're using the Meade 16-inch, which is not pictured here. What's pictured here is the classic 35-centimeter vacuum solar telescope. So we're observing the sun, but one big difference between the sun now versus the sun back around 2000 is that the sun is very quiet now. And so since our focus with both observatories is to focus in on the active regions and their evolution and flaring activity, we haven't had much to look at. So basically we're just capturing high resolution mosaics of the sun. And these are two examples that were taken back in early March at the edge of the sun. And then also near the center, we can see the hydrogen alpha texture. One advantage of a quiet sun is that it's easier to get flat field frames. The center of the sun, we can use that to produce several images slightly offset from one another, average them together, and use that as a flat field for our solar images. We're also doing lunar and planetary observations. We have these images of the moon that were taken actually during the afternoon. We have a couple of filters to decrease the light of the moon to make it more bearable for the camera to capture and not get saturated. We use an S-Big 1600 camera currently for our imaging capabilities. So we also have a deep sky imaging. These are monochrome short exposure images. I've actually taken a number of such images of different deep sky objects and comets. And so these are just a couple of images. One of the things that I thought was cool about these images is that they're kind of a few steps up of what somebody would visually see through a large telescope from a dark site. And so I can show these to my students and I can explain to them these are sort of what we would see under very good conditions with a very large scope. The reason why these images are so much different than the Hubble images, I can explain to them why that is. But we do have equipment and resources available that we will be starting to do color imaging and narrow band imaging of different targets. As a matter of fact, we have a wish list of different projects that we want to get involved with this observatory. So, and these are just some more examples of some images that I've taken. These are just simple 30 to 60 second exposures of these regions. And so we work under a less than ideal sky. It's a Bortle class 6 sky. And so we have to deal with some light pollution, but I anticipate that we can get around that by using narrowband capabilities. So what's next? We have a couple of example images that our co-author, Doug Holland, who's going to be working with us this summer. He's taken some LRGB images. We see one example of M78 in the upper right corner and the Eagle Nebula in the lower right corner, where he's used narrowband filters in order to capture this multicolor image of the Eagle Nebula. So he plans to bring in his expertise with his work, his experience with his work with NASA and these special cameras that he's designed, high resolution CMOS cameras that he's designed. We're going to actually be using them on our telescopes to take high resolution narrowband images of the emission regions and select targets in the sky. So again, we have a lot of projects that we have on our wish list that we would like to pursue with this observatory. We also want to make our facilities accessible to local astronomy clubs and interested members of the public, including any citizen scientists that might want to make use of the telescopes in order to increase their citizen science capability. So it's kind of hard to keep all this within 5 minutes. I tried the best that I can, but you can see more details in the write-up for this project. Ultimately, we do plan to make these telescopes robotic so that we can control them from anywhere. Right now, we have to be on site in order to control them. But again, we're working through some issues with the CDK. We hope to have first light from that telescope sometime later this summer or early in the fall. We have been observing with the MEAT 16-inch for almost a year now, both daytime. The Flux calibration is something that is up and coming. We plan to use this special, what's called LabSphere calibration sources to investigate ways of flux calibrating our data to augment our photometric capability. So in the interest of time, I'll go ahead and end it with that. And again, if you have any questions, you can either email me or ask if we have any time right now, or you can email me. And if you're in the Houston area, you want to come check it out, you're welcome to come by to do so. Thank you very much.
Thank you, Brian. Wayne, any questions for Brian?
We have no questions and no hands raised.
Okay. Well, Brian, thank you very much. And
we just got a question.
Wayne, can I break in for a minute?
Yes.
I have a proposition. Since we are kind of over time, I would like to get the opinion of our current audience about how rigidly we should have tried to stick with the schedule. And then after this poll, we can continue with questions for as long as anybody wants. Does that sound okay?
Sounds good.
Okay. I am launching the poll. Now, of course, the panelists don't get to vote, but we've had vigorous discussion after the talks today. I think it's pretty neat that we can get the worldwide community together to talk about these things. But if the audience would please pick your opinion. Should we set the schedule and stick with it, cutting off discussion as needed for our future meetings, or should we be flexible and kind of at least stay within plus or minus 30 minutes of the schedule, or kind of let things go as the thing happens? I'll set my timer for 10 seconds and we'll cut it off at that. So vote now. Okay, now I have to figure out how to show the responses. Okay, I'm closing the polls and then share the results. I hope everybody can see that.
No.
Looks like we have a pretty strong consensus that be flexible, but start each talk within plus or minus 30 minutes of its scheduled start time. Anytime you give 3 answers, everybody picks the middle one, right? Okay, we will use that information for planning the agenda for the next 2 meetings. I will close that and hand everything back to Jerry.
Okay.
So Bob, we have a few minutes, as we say, for those that have to leave. They're pretty much, I think we've kind of reached, you got to go, you got to go. But how about opening it up for just an open discussion with the panel? I have a couple of questions queued up for Joyce Guzik.
Okay, let's bring Joyce back on.
And so Albert Smith had a question. Let's see if we get his microphone open here. Albert, you with us? Oh.
Yes, hello, Joyce.
Joyce, you're muted.
Okay, now I'm unmuted. Okay, thank you.
Yeah, I think you may have touched on my question later on after I submitted my question regarding HR 7403 and accretion. I was interested if more was being looked at the possibility of accretion being responsible for pulsations among binary systems.
Well, accretion driving pulsations or being responsible for pulsations. So was 7403, was that the one with the decretion disk?
Yeah, yes.
I don't even remember now. There's so many numbers. Okay.
You see any more of those?
They are looking at, for that one, well, it isn't accretion, but no, I don't know. I don't know if I can give you a specific example of any star where they're looking at how accretion may drive pulsations. They are looking at how tidal effects drive pulsations. And if stars are fairly close together in binaries, then the tidal effects can drive pulsations. That is a very active topic. But the accretion disk, I'm not sure.
Thank you.
Thank you for the question.
Sebastian Otero had a question. Let's see if I can find his microphone here. Not finding it there. See if we can get this back up.
I'm
sorry,
unmuted.
Sebastian.
Yeah, I am unmuted now.
There we go. Thank you.
Okay. Regarding the hybrid star falling outside of the predicted area in the HR diagram, have you ruled out any blending issue because we have received several star submissions to VSX with multiple variability types based on test data, and it turned out that sometimes a nearby star was actually responsible for one of the variations. So is there a chance that we are seeing something like that here?
There is a chance. There's a lot of stars that would have to be investigated for blending and have it ruled out, but in some cases, I think that's quite possible, especially for those ones that show hybrid pulsations, because the low frequency cycle per day could be a star in the background or a binary background, and on a case-by-case basis, you do have to look at that and try to find, to rule that out. So yeah, I think in some cases that is possible, especially the ones that show the gamma Doradus-like periods. Yeah.
Okay, thanks. Once I remember that we received a submission with 2 stars separated by 45 seconds, and they were still blended. So there's a chance. Yes. Thank you.
Yes. No, that's very important. So that's something that that ground-based observers could help with, is looking at these stars individually and trying to determine, or even just re-reducing the data and seeing if you can find a blend. But as we saw in the talk right before me, the test pixels are bigger than the Kepler ones, and they're bigger than a lot of things. So there could be blends in that data. Yes.
Thanks.
So yeah, we could use that help to rule that out.
Joyce, this is Wayne Green. There's a number of small telescope spectroscopists in the audience. I noticed that most of your stars were right in our magnitude range. Do you see any means for us to participate?
I do. There are, in those Beta Cephei and slowly pulsating B stars, they were first observed to be pulsators or varying in line profile variations. And it would be interesting to look at those again and see if we can confirm that there, and even find some frequencies that you can see spectroscopically. Are those the same or different than frequencies you can find photometrically? And also spectroscopy can help us, especially and even multicolor photometry can help us with distinguishing between a pulsation and some other cause of variability, or to even do mode identification. Is it an L equal 1, a dipole mode, or a quadrupole mode, an L of 2 mode? And that's the kind of information that the modelers really need to be able to use as constraints for their stellar models and their pulsation models. So yes, there's a lot of opportunity.
We worked mostly at about the R600 level, and even there photometrically with the spectrum, we have the ability with a very broad slit to increase exposure time, but to give essentially the analog of photometric filters all in one go. And the second resolution that we typically work out is somewhere around the 1000 to 1500 range.
Mm-hmm.
Okay, thank you.
Thank you. Well, yeah, I know very little about that kind of observing, but I know when I started my career, it was mostly stellar modeling, and I need those kinds of constraints. So getting those from spectroscopy would be really, really valuable. And
I think we'll be in touch.
Even being able to tell if the temperature is correct. Sometimes doing another spectra and better data reduction changes the temperature by hundreds of degrees and can move the star into where we think it should be. Okay.
All right. Any other questions for for Joyce or any other panels speakers today? Well, that concludes day 3 of the SAS-AAVSO webinar, and I look forward to looking at you next Saturday at noon, or 1800 UT. Also, I want to, before everybody goes, I want to emphasize to look at the handouts that are available. There's some, the proceedings are there. There's some really nice opportunity if you're interested in the products of DC3 Dreams, which is ACP and scheduler. There's some Software Bisque has some flyer out there for some of their products, and we have the session agendas on there also. So take a look at those, and we'll see you next Saturday. Bob, do you have anything more?
Thank you, everybody. On next Saturday, the first session up is the AAVSO meeting. I want to emphasize that's open to everybody who's interested. So we'll see you then.
Also, thank you to all the speakers and all the organizers today. That was an awesome. No, I'm not going to turn on I don't have the bandwidth.
You're not going to turn your camera on.
I don't have the bandwidth here. I'm going to cut off. But thank you all for participating. It was great to virtually see you and hear all about really cool projects and really cool research. As Bob Buckheim mentioned, we are having the AAVSO meeting next week, where our president is going to discuss a strategic planning process and talk a little bit more about where the AAVSO is heading in the future. Before that, we'll have an informal meet and greet, so look for your email with the Zoom link for that one, and come join us and chat and hang out. From me, again, congratulations to the speakers and to the organizers for a very successful, very successful third day. And I'm looking forward to the next weekend when we will all get together and discuss science again.